Yes, I think it's not ICMS turn. Okay, it seems we are now. Yes, we are. Yes, I think it's not ICMS turn off. Yes, so if you want to have a look, it's there. With, I don't remember how around 30 seconds delay between the Zoom and the YouTube channels.
Yeah, I've got it up now anyway. So if I see any questions popping up, I'll try to keep an eye on both.
Fine. 8:52. Okay, then I have time to eat, so I'm sorry.
Yeah, no, it's okay.
Bon appetit.
Yeah, it's lunchtime. I've got a cup of tea as well. I was thinking for timings, I'll probably just because I think I've got access to the hand up to put a hand up as well. So about 5 minutes before the end of the 25 minutes, I'll just press that so you can so you know you've got 5 minutes left.
Okay, good.
And that'll save me from having to interrupt and just so you can it won't disrupt the flow. Yeah.
Go back with some coffee.
Oh yeah, absolutely.
You look very professional, Matteo.
Professional. Thanks very much.
It's the chair that makes too professional, but I risk to fall asleep because it goes back and
Yeah.
to fall asleep. That's why I need to stay up to remember to wake up.
No, because we have participated together to some conferences in the last month, but I was used to see you at home. So
Yeah, because now it's one of the few times I'm in the LPTM, so that's why.
Where are you now, Matteo?
Cergy-Pontoise, LPTM.
Okay. And you have a permanent position? Or
No,
postdoc
postdoc
position?
with Alessandro Torcini.
Ah, okay. I understand.
You know, actually, this is his office, actually, and that's why.
Very nice. Yeah, I'm just at home, still working. So not very professional background. I should have it blurred out, really.
Yeah, often I do from home, but this time is.
I also have works. I also have workers at work in this moment. So I hope they will not use. They will not make too much noise.
Ah, okay.
Because you have to look at them and push them to work. You know, you cannot leave the apartment.
Inside home.
Yeah. That's,
Ah, okay.
there is just a wall dividing me from them. So.
Okay.
So just got to wait for Tilo.
So one question: are there some parallel? So there are other parallel symposiums.
Yeah, so there's two others going on at the same time.
Okay, I see.
Yeah, so there's a trace. Hi there, Tilo.
Hi.
Hello.
Hi.
Yeah. Well, yeah, we'll start in 5 minutes. We're just waiting for Denise to come. But yeah, I was just saying to you though that 5 minutes before the end, so the end of the 25 minutes in your talk, I'll just raise my hand, just to say that, just to let you know that you've got just 5 minutes left.
Okay.
Just to stop you having to jump in and interrupt the flow.
Okay. Will I be able to share my screen, or should
Yeah,
I?
if you want to. Oh, well, I think actually Etienne might need to make you a co-host. I think he's just gone to get some coffee, but he'll be back in a bit, and then I think he'll give you those admin rights, and then you'll be able to share your screen.
Okay, then I probably don't have to test this.
Yeah, well, unless I can do it, maybe.
Oh, I think you can do.
I think you can do this. But no, I cannot.
No, I don't think so. I think we have to wait for Etienne to come
Yes,
back.
only the host can, I think. Co-hosts cannot.
So your collaborator Helgard gave a talk on the working memory stuff, Simona. It was really interesting. I thought is yours going to be like crossover with a bit of that?
Well, I mean, I don't know if you did you had some questions for him. Unfortunately, I was traveling on Monday, so I was completely out.
I would say,
yeah.
That's fair enough. Oh, Etienne, I think Thilo's joined us now.
Okay, hi, Joe.
Hi.
You should be able to share your screen now. And can you remind me the fourth speaker, Michael?
Yeah, so it'll go Thilo and then Simona, and then I think it's Matteo. Yeah, then Matteo, then Denise.
I don't see.
Dennis.
He's not in the room.
No, not yet.
Should I share my screen? Sorry.
No, I just start to record so that I don't forget. So now our conversation is recorded.
Very good. Yeah, perhaps if you could keep an eye on the participant list, Etienne, and then when Dennis arrives, he can just make him a co-host.
Yes, I will give him the rights. Fine.
Yeah, fantastic. Okay, well, I think we're coming up to 3 p.m. now, so I'll I'll do my duty as host. And
should I share or?
Yeah, if you'd like to share, Thilo. That's fantastic. Yeah, I can see that fine. Okay, so thank you everyone for coming to this mini symposium on the subject of next generation neural mass models. We have our first speaker today, Thilo Schwalger from TU Berlin. So please, whenever you're ready, Thilo.
Yeah, hello everybody. Thank you, Michael, for setting up this wonderful mini symposium on next generation neural mass models, and for giving me the opportunity to present this very recent work about this work that we have recently uploaded on arXiv, and it arose from an exciting collaboration with Valentin Schmutz from the EPFL in Lausanne and Eva Löcherbach from Paris. In general, we are interested in neural population dynamics, and one basic question is the following. So consider a population of n neurons, that may receive some external stimulus. And then we may ask, what is the response of this population to this external stimulus? And that means, what is the neural activity? And from a microscopic point of view, the neural activity are the spikes of each neuron. In general, the prediction of these spikes is very complicated because we have a complex system. So we may want to reduce the complexity and simplify and only look at the population activity. So we may ask, what is the population activity, meaning the total number of spikes of the population in some small time bin? And can we characterize the dynamics of this population activity at this mesoscopic or macroscopic scale? So to be concrete, in this work, we consider a network of leaky integrate and fire neurons with escape noise. And this model is given by the membrane potential of UIT, so of each neuron I. It is driven by some external drive mu of t. There's a leak current. Then there is a term that corresponds to the reset whenever the neuron makes a spike. So the membrane potential is reset to 0 in this case. And we have the recurrent synaptic input from the other neurons. And it's a fully connected network that we consider with connection strength J/N. And spikes are generated stochastically with a stochastic intensity f of UIT. And this can be formally written using these Poisson random measures PI, using this integral with the intensity written in the indicator function. So Zi of t is the spike count of neuron I. That is an important quantity in this model. So this model is quite standard in theoretical neuroscience. So it has been pioneered by Wolfram Gerstner in 2000, but has also been used later many times. Among others, we saw on Monday in the talk by Quentin Cormier a very similar model. Okay, so let's look at this at simulations of this model. So here I simulated 200 leaky integrate and fire neurons that were synchronized at time t = 0. So it means all neurons had a spike at 0. And then we see a period of silence. So that's a refractory period because neurons have some relative refractoriness in this integrate and fire model. Then, with sufficiently strong drive, neurons will spike when the refractoriness has faded away. And then neurons fall again into a refractory period. And this oscillating pattern can be better seen by looking at the population activity, which is defined at the total number of spikes in some small time step t plus h divided by h and the number of neurons. And this is plotted here, and you see these damped oscillations. How to characterize this population activity? So one way that is very popular in computation in neuroscience is to consider heuristic firing rate or neural mass models. And the classical firing rate model looks like this. So we have a first order dynamics for some variable ut, it could be called input potential. And this is driven by external current and by the mean field input from the network. Then this input potential is passed through some nonlinear function that is usually taken to be the steady state transfer function of the single neurons. That means the Fi curve. This model very well reproduces the mean stationary activity by construction. However, this model fails to reproduce the the transient dynamics, so the non-stationary dynamics. It doesn't capture the damped oscillations. And it also fails to describe the fluctuations that are due to a finite number of neurons. We have only 200 neurons here in this population. So we see these finite size fluctuations, and describing these fluctuations is very important in biology, because the number of cells of a given type at a given location in the cortical microcircuit is not so huge, but maybe a couple of hundred neurons per cell type and location. Okay, so we want to address these two problems. So the first problem, so how to get the transient dynamics right, is, I think, well understood. And in general, this to get this transient dynamics, one needs to have a description in terms of a partial differential equation or an integral equation. So it's an infinite dimensional dynamics. And several theoreticians came up with a population density equation that describes the density of the membrane potential. And also it has been mathematically proven that the system for a population that has infinitely many neurons, so in the limit n to infinity, converges to this PDE here. This PDE basically is a continuity equation where you here recognize the deterministic drift. Then there's a non-local term corresponding to the mean field interaction, and there's a sinc term that corresponds to neurons spiking at membrane potential u with intensity f of u. Then we also have a jump of the density at voltage 0 at the reset potential because of the reset. Okay, so then we have this quantity rho t of f, which is the total flux due to spiking. So it's the spikes from all neurons with all possible membrane potentials. And this total flux due to spiking is exactly the population activity. And one point that I want to stress here is that we have a conservation law, namely that this density rho is normalized to unity at all times. Yeah, and this reflects some that the number of neurons is conserved in the population, is constant. Another equivalent point of view is the integral equation picture. And this has a quite intuitive representation. So imagine that we have simulated the population activity until time t, and we ask, what is the activity or number of neurons that spike in the next time step? To get this, it is useful to consider the last spike time of the neurons. And we may ask, what is the number of neurons that had a certain last spike time? So consider a given time t hat. And at this time t hat, there were a of t hat neurons that had a spike. Now, if you multiply the number of neurons that had a spike at this spike time t hat with the so-called survival probability, so the probability that the neurons did not fire between time t hat and time t, then this gives the fraction of neurons that had their last spike at time t hat. Yeah, so S times A would be the density of the last spike times. And each last spike time has a unique firing rate lambda t hat that can be used to construct the total firing rate at time t, namely by this integral. So we have here the number of neurons with last spike time t hat, so it's S times A. And these neurons, they fire with rate lambda. And if you sum up over, or if you integrate over all possible last spike times, then we get the total activity at time t. Yeah. Okay. Again, I want to stress a conservation law here. Namely, that the integral over this density of last spikes is unity, which just expresses that the total number of neurons is conserved because each neuron only contributes one last spike time. And I say this because for the finite size case, this conservation law will no longer hold. It will only hold approximately. And it has some consequences for understanding the stability of the processes. Okay, so this was an introduction. I will now talk about a mesoscopic extension, so an extension to finite number of neurons. And then in the main part, I will talk about the stability of this mesoscopic model. Okay, so let's first do the extension to N. So I will first give you a wrong picture or a wrong model, like a naive approach. So in this naive approach, we could say we have this integral that gives this integral equation, and A of S ds would be the fraction of spikes, well, the total number of spikes in an interval S to S plus ds. Divided by the number of neurons. Now for finite size, this is not a deterministic quantity anymore, but we could say that the total number of spikes in this interval is a Poisson random number with an intensity given by the population activity multiplied with the number of neurons. And then we need to normalize this with the number of neurons, this Poisson number. Okay, let's do this. So we get this Poisson number or this counting process. We divide by 1. We multiply with 1 over n just to get it per neuron. And here we have a process, a count process with intensity n times a bar. That is driven by a single Poisson random measure, pi. And this equation for the population firing rate is the same as the one for n to infinity, but we replace this term by dz, by the increment of this spike count. And then the distributional derivative of this per neuron spike count could be interpreted as the finite size analogon of the population activity. So it can be represented as a sum of Dirac delta functions centered at the jump times and divided by n. So let's simulate this model and see how it works, this naive model. So I remind you that this is the picture of the microscopic model, and simulating the naive model, we get very well these transient dynamics in the beginning. So we see these damped oscillations. So that's very nice. So it captures the effect of the refractoriness. However, we have a problem, and this can be seen if you simulate longer. So if you simulate now not 300 milliseconds but 20 seconds, then at some point, so we first see that the rates, they go somehow crazy, they go up to 150 hertz, but then at some point they also hit 0, and then when they hit 0, they stick to 0 and the network basically dies out. So the network activity is silent at some point. So that means that there's no stationary solution that is non-silent here in this model, which is obviously not very good. So how to make it better? So a few years ago, I derived with some approximations a mesoscopic model that looks very similar. So I derived it directly from the microscopic model of integrated and fire neurons. And it looks like this. So it's essentially like the naive model, with the only difference that we have here a correction term. So we will call this correction term, and we also need, so now this activity could become negative, this intensity, so we need to rectify this to get positive intensities. Okay, so we have this correction term and a prefactor lambda. So lambda depends on the past activity, so there's a explicit formula for this dependence. However, for the sake of the talk, we will consider lambda to be constant and strictly positive. And the case lambda equals 0 will be called the naive model, yeah, because then we don't have this term and we end up with the naive model. Okay, and we recognize here the analogon of this conserved quantity that is unity for the n to infinity limit. So for n to infinity, this integral becomes 1, so we don't have this correction term. And somehow it seems that by this correction term, the model always, wait, first I have to say that this term is no longer exactly equal to 1. Yeah, so it's a stochastic quantity. You can see this in simulation. However, it's constructed somehow in this way that the dynamics always tries to make this integral close to 1, yeah, to keep this close to 1. Yeah? But this is a property that is not well understood yet. Yeah? That we never understood why this works. Yeah? Okay, so we have this mesoscopic model, and we can simulate this also. By the way, there are quite efficient simulation algorithms where you can integrate a stochastic rate model very quickly. So we have again this microscopic model and the transient dynamics, and we see that the mesoscopic model also gets the oscillations right. And if we simulate a long time, 20 seconds, we also see that it's kind of a stable rate. So it doesn't seem to die out, and I never observed that this model dies out in simulations. And what is more, what is really nice about this model, that the fluctuations are very well captured. So the temporal structure, and this can be seen by looking at the power spectrum. So here you see the power spectrum of the population activity of the microscopic model. So that describes really the temporal autocorrelations, but in frequency domain. And in blue you see the power spectrum of the mesoscopic model, and it has it matches this very precisely. So the temporal structure is kept in the mesoscopic model. So the single neuron dynamics that gives rise to correlations in the spike trains is captured by this mesoscopic model. So that was one population. One can also extend this to multiple populations and also to cases where we have interesting dynamics. This model goes really beyond linear noise approximation. So it captures, for example, the statistics in a multi-attractor model. Here's an example where we have 3 populations. It has a bistable dynamics. If you simulate the microscopic network, it would show this hopping between the 2 attractors. And if you simulate the mesoscopic integral equation, you also see this hopping. And in fact, the statistics of the time series are very well matched. So you see that in the power spectrum, but also in the waiting times in one attractor, they are also very close. So now that's nice. Let's discuss the stability properties here. So let me first give you some heuristic arguments. So because we have no rigorous analytical handle on the stability so far. We just observed this in numerics that it behaves well. So the first interesting point is that the model looks very is very closely related to a nonlinear Hawkes process. And in fact, for the case of no coupling and a constant external drive, one can rearrange term and write this process exactly in form of a nonlinear Hawkes process, where this term is the self-interaction kernel. Now, this is very insightful because if this factor lambda is positive, as in our mesoscopic model, then it turns out that the total mass of this interaction kernel is smaller than unity, which means that the Hawkes process is stable. On the contrary, if lambda is equal to 0, corresponding to the naive model, the total mass is exactly equal to 1. So we obtain a critical linear Hawkes process. And this means that for our specific choice of the kernel, there is no non-silent stationary solution. So now the question is whether also in the general case where we have coupling, we can use these methods from nonlinear Hawkes processes to say something about the stability. So another point of view is to look at the neural mass and the conservation of the number of neurons. That seems to be important, and see whether it really stabilizes around unity. So for this, to this end, we introduce this neural mass, m of t, and consider some hitting time, that is the time until the rate first hits 0. Then one can show that this neural mass obeys the following stochastic dynamics, which looks somehow analogous to an Ornstein-Uhlenbeck process. However, it's a more complicated process because this dz tilde depends on the mesoscopic dynamics, on the stochastic integral equation that runs in the background of this process. Nevertheless, we can learn a lot from this process. So first, we see here that we have some kind of deterministic drift term that always tries to bring the system to unity. Yeah, and in fact, if we plot in simulations this neural mass, then we see that it fluctuates around a unity for the mesoscopic model, and also somehow in the beginning for the naive model. However, if we simulate a longer time, then we see that this neural mass goes very large, and also will go to 0 for the naive model, whereas for the mesoscopic model it really tightly fluctuates around unity. So that reflects the conservation of neural mass that should be there. Yeah. So that's one thing, and the second thing is one can also show that once the rate goes to 0, the naive model stays at 0. So the neural mass will sticks to 0. So there is no non-zero stationary solution for this process. Yeah. So this neural mass, or this quantity, turns out to be useful for constructing a Lyapunov function if we regard the process as a Markov process. So we may also think of stability in terms of Markov processes. Okay, and let me finally give you some more the rigorous results that we obtain, so we can write this process as a piecewise deterministic Markov process. I will not go into detail, and then we can define what we mean with stability for this Markov process, and we define stability in variation, which means that there exists a stationary solution, rho bar, nu bar, such that for all measured valued random initial conditions you had, we have a density that couples to the that is driven by the same Poisson random measure, but with the different initial condition. And then the associated jump processes, they couple. That means that there exists a finite time such that the spikes are the same of the two processes. So the spike trains, they couple to each other from some finite time t onwards. And this is my last slide, so we can make some rigorous proofs. You can find the proofs in this archive paper. There are some assumptions. We first prove that the process is non-explosive, so it's well posed. We use for this the Foster-Lyapunov inequality, so main Tweedy theory. And then we show that if you have two processes, two solutions of the PDE with different initial conditions, but with the same Poisson random measure, that they couple, so that the associated jump process couple almost surely in finite time. And then we show that there exists a non-silent stationary process that solves this SPDE. And with this, basically we can show that the voltage structured SPDE is stable in variations, so that there exists a unique stationary solution to our mesoscopic model. Okay, so let me summarize. I first showed that the finite size neural population model accurately captures the fluctuation statistics and the transient oscillations due to refractoriness. Then I showed that the naive mesoscopic model without the correction term does not exhibit a stationary solution except the silent solution. It stays silent once the stochastic intensity hits 0. And for J, for no coupling, it's a critical linear Hawkes process. And finally, the full mesoscopic model, so with lambda larger than 0, is stable in the sense that it exhibits a unique non-silent stationary solution. And the proofs that we use is a mixture of methods from nonlinear Hawkes processes and Markov theory. And if you want to learn more about this work, please have a look at our archive paper. Thank you very much.
Thanks very much, Thilo. That was very interesting. Are there any questions? And please just raise your hand if you had one. Oh, I think Etienne's got a question.
Okay, thank you, Thilo. I have a very naive question. Are you able to evaluate the size of your correction term as a function of the time and your capital N, the size of the particle system?
Of the population?
Yeah, the size of the population.
Yeah, so one can show that this the size of the correction term. Yeah, so this correction term was this lambda 1 minus the neural mass, and one can show that this we can show a certain recurrence property for this neural mass using the Foster-Lyapunov inequality. So that's the main Tweedy theory for Markov processes. So it means somehow that the process comes back to some ball in some finite time. So
maybe to be more precise, at time t equal to 0, the correction is equal to 0. Am I right?
That's right. Yes.
Okay, and as time increases, it becomes non-zero. Mm-hmm. But the time at which it's a macroscopic quantity, I guess it depends on the size of the particle system, the number of neurons.
Yes.
Is it 1 over root of n, 1 over n?
Yes.
Something else?
Yes. I think this goes to 0 as 1 over square root n.
Okay. Thank you.
Thank you very much. I think in the interest of time, we should probably go off to our next speaker. So please, Simona, whenever you're ready, Simona Olney will start her talk.
Okay. Okay, thanks a lot for the invitation. I'm going to present a paper that I've done in collaboration with Marco Segneri on GB and Alessandro Torcini regarding theta-nested gamma oscillations in next generation neural mass models. As you can infer from the title, I'm going to speak about the coupling between neural rhythms that are considered to be a backbone of information coding. And in particular, I will concentrate on slow oscillating theta band and on fast gamma rhythms. And in particular, I will start the starting point of this work are recent optogenetic experiments that revealed that there is a coupling between neural rhythms in rodent brain areas. In order to reproduce the experimental results, we have applied a recently developed neural mass model, which was analytically obtained from the microscopic dynamics of a spiking network, which is able to autonomously generate oscillations with frequencies that are controlled by synaptic timescales. In order to explain the emergence of this coupling between rhythms, we have investigated two different mechanisms: the pyramidal interneural network gamma, which is called commonly ping mechanisms, and the interneural network gamma, so the ing mechanisms. Both mechanisms have been invoked to explain essentially locally generated gamma oscillations, and you will see that within our experiment numerical results, both mechanisms give rise to theta-nested gamma oscillations with almost identical feature. Between entering into the details of the talk, I would like to give you some nomenclature, and for those of you that are not expert, let me say, in all the names regarding the oscillatory coupling mechanisms, I will just present you some of the possible oscillatory coupling mechanisms. So, for example, we can speak about phase-phase coupling, as you can see here, between two gamma oscillations, where we have phase coupling between the signals that are emitted by two different areas. We can observe also cross-frequency phase amplitude coupling, that essentially means that the envelope of the gamma waves is modulated by the common theta rhythm. Then it is possible also to observe whenever we are, as in this case, in presence of two areas that are emitting gamma oscillations and that are coupled with the slow with an area which emits a slow theta frequency, so we can observe phase-phase coupling between the two red areas. And finally, we can observe also cross-frequency phase-phase coupling, where the phases of theta gamma oscillations are correlated. So, as I was saying in the second slide, in the outline of the talk, we started from some optogenetic experiments that were performed by Butler and co-authors and that are published in the Journal of Neuroscience in 2016. Essentially, the authors recorded extracellular field activity in parts of the hippocampus, both in vivo and in vitro. In particular, in vivo, they have recorded the extracellular field activity in the stratum pyramidale from an anesthetized head-fixed wild-type mouse, and in vitro, they have considered acute brain slices that were expressing CHR2 in the CA1. In both cases, oscillations were phase amplitude coupled to the theta stimulation, as you can see here, occurring at the peak of each sinusoidal stimulation cycle. Oscillations, most importantly, were stable, as you can observe here, and persisted as long as the light stimulation continued. So immediately stopping, as you can see here, when the light stimulation stopped. So these are some results that I will discuss later in detail, comparing with the numerical results. So I don't want to enter into the details of all these slides, of all these panels in this moment, just to say that these are the results that were obtained in vitro. So we will essentially compare our numerical results with the in vitro results. And the main point that I would like to highlight regarding this slide is that in this experiment, the authors observed that theta gamma phase capping increases with the theta input, and essentially while the power of the gamma oscillations is highly dependent on the theta input, as you can see from all these panels, the frequency range essentially did not shift when either the frequency of the power of the theta input was varied. So it's really a resilient effect. So let me start from the model that we have used to simulate the network dynamics, so the microscopic model. We started using quadratic integrate and fire neurons globally coupled. In particular, as I told you, we used two different setups, the ping setup and the Ying setup. In the ping setup, as you can see, we considered a first order differential equation for the excitatory population, describing the evolution of the membrane potential, a first order differential equation for the membrane potential of the inhibitory network. And what is important to highlight in this slide is that the neurons were globally coupled and they interacted via excitatory and inhibitory postsynaptic potential with the delta profile. And the synaptic field is described for both populations by this term. Then regarding the Ying setup that you can see is described by this topology, we will take into account the first order differential equation for the membrane potential of the inhibitory population, but in this case, the neurons are still globally coupled, but they are interacting via an inhibitory postsynaptic potential with an exponential profile, because this is the only way we are able to observe the emergence of collective oscillations in a purely inhibitory network. So this means that we will also have a second first order differential equation taking into account the evolution of the synaptic field. So in order to develop a neural mass model, let's start taking into account the macroscopic network variables that we can derive from the microscopic model. That will be the one that we will compare with when developing the neural mass models. So in particular, the macroscopic network variables that we can construct are the average population activity of the network and the average membrane potential. Then we can construct the neural mass model, the mean field model, by taking the infinite size limit, writing down the continuity equation for the probability flux. The continuity equation can be solved by thanks to two main assumptions. The first assumption, the so-called Lorentzian ansatz, means that the solutions of the continuity equations has to converge to a Lorentzian shaped function of this type. But this is not sufficient to obtain a reduction in dimensionality of the ordinary differential equations and to jump to a low dimensional system of first order differential equations. In order to have the reduction in dimensionality, we also have to assume that the distribution of the excitabilities has to be distributed according to Lorentzian probability density function. And just to highlight you some variables and parameters that will be used in the following slides, H, which is reported here, is the median, and delta is the half-width, half-maximum of the Lorentzian probability distribution function. So the neural mass model that we will use are this one. In case of the ping model, we have two differential equations for the instantaneous firing rate and the average membrane potential for the excitatory network, and other two for the inhibitory network. On the other way, when we consider the Ying setup, we have two first-order differential equations from the instantaneous firing rate and the average membrane potential for the inhibitory network only, plus the evolution of the mean synaptic activity. In these equations are reported also two terms that are related to Gaussian, additive Gaussian white noise that for the moment will not be used. So I will tell you, we will add the Gaussian white noise just in the last slides. So for the moment, this is not considered. Okay, let's start from the situation where there is no external drive. So which is the dynamics that emerges in this kind of systems. Let's start from the ping setup. In the absence of external drive, it is possible to observe two different kind of dynamics, the asynchronous state and the collective oscillation state. And it is possible to pass from the asynchronous state that you can see here from the raster plot is described by scattered spiking activity to the collective oscillations via bifurcations that can be obtained both increasing the excitability of the excitatory population or the excitability parameter of the inhibitory populations. During the collective oscillations, we observe bursting activity both in the excitatory and in the inhibitory network, and a clear characteristics of the ping setup is that the excitatory population fires before the inhibitory population. And as you can see, the delay between the excitatory and inhibitory bursts is always present independently of the value of the excitability chosen, and even though it decreases by increasing the excitability value. If we take into account then the ink setup, we see more or less the same framework, because in the absence of the external drive, we pass from the asynchronous to the collective oscillation state by increasing the excitability parameter. And also in this case, we pass from an asynchronous firing to a bursting periodic activity. Collective oscillations are within the gamma range, and we can see in this case that by increasing the excitability parameter for the inhibitory population, we observe a linear increase of the frequency of these oscillations. Then let's add the theta forcing. So we start from a situation for the unforced system, which is the asynchronous state, but being aware of the fact that you have to be nearby the bifurcation in order to let the theta forcing drive the system into the collective oscillation regime. So we can see that whenever the theta forcing is switched on, both for the ping setup and for the ing setup, we observe an emergence of collective oscillations. And if we look into the details, we observe that the amplitudes are modulated by the amplitude of the forcing term. Therefore, we are in the presence of the so-called phase amplitude coupling that I've introduced you some slides ago. And then if we look at the heat maps of the systems, we observe that the gamma range with the maximum power localized around 50-60 Hz, as you can see, both for the ping setup and for the ing setup. And as seen in the experimental setup, the oscillations are stable and they survive until the forcing is on. When the forcing is off, they stop. So in order to get into the details of the locking, we have also investigated the wavelet analysis for the ping and for the ing setups that confirm that collective oscillations are in the gamma range, and that allowed us also to get more details regarding the microscopic and macroscopic dynamics. In particular, wavelet spectrograms has been averaged over many theta periods. And we've seen a peculiar difference between the ping activity and the ing activity because they are essentially unchanged for the ping case. So independent of the theta period, they show always the same emergent frequency for the collective oscillations, meaning that there is periodicity underlying the dynamics, while they smears out for the ing setup. So meaning that for different theta periods, the emergent gamma oscillation is has a slight different frequency. So meaning that the underlying dynamics is quasi-periodic or chaotic. If then we compare with the experimental setup, we see that the experimental spectrogram always shows the correlations among the theta phase and the gamma oscillation, but it is highly asymmetric. So what we can say is that probably the bifurcation that is associated to the emergence of collective oscillations in the experiment is probably hysteretic, and it is confirmed by the fact that taking into account this hysteretic transition, so that we have also observed in the ping setup, we obtain effectively a asymmetric spectrogram. So, getting more in detail of the dynamics by varying the amplitude of the external forcing, we see that essentially the dynamics is usually quasi-periodic. And I can affirm that it is usually quasi-periodic looking at the maximum Lyapunov exponent, which is quite always 0. There are also different locked states that emerge, in particular M1 locked state that are called, that we call theta-nested gamma oscillations, where essentially, as you can see here, for one theta oscillation, we observe M, which in this case is 6, M maxima in the population activity that appear. In addition to the locked state, we also observe the locking M to N that are a little bit more complex, where M maxima in the population activity appear every N theta oscillations. Curiously, for the ing setup, we observe also a point where the maximum Lyapunov exponent is positive, so meaning that there is also chaos appearing. Then if we concentrate on the theta-nested gamma oscillations that were also the main focus of the experimental findings, we see that locked state, this kind of locked state in the ping configuration occur in separated stripe, while they appear in as a continuum in the ing setup. So meaning that essentially for the ing setup, it is easier to observe locking activity. From now on, I will somehow compare our numerical results with the experimental findings, entering into the details of all the panels that I've shown you very briefly while presenting the experiments performed by Butler and co-authors. In particular, in this slide, I will show you, I will try to convince you that the emergence of theta-nested gamma oscillation are really resilient independently of varying the frequency of the stimulation. You see the stimulation, the external optogenetic stimulations in the experiments is given by this blue curve. And also in our numerical setup is given by this blue curve. So by varying the frequency of the external forcing, or by varying here the amplitude of the external forcing, the theta-nested gamma oscillations survive and are resilient. And also we can see, we can say that phase amplitude coupling is present for all frequency and amplitudes investigated. And then the number, if you look at this, the number of nested oscillations in each cycle increases for decreasing the frequency of the external stimulation. This is true not only for the experiments, but also for the numerical investigation in the ping and in the ing model. And then if you look at the gamma oscillations amplitude, you can see that they increase proportionally to the amplitude of the external stimulation. What differs on the other end are power spectra. In particular, you can see that the spectra of obtained from optogenetic stimulation present only two peaks, the stimulation frequency and the one associated with the gamma oscillations, but the spectra are the same both for the in vivo and the in vitro experiments. If we look at our power spectra, we see that we still see the stimulation frequency here and the stimulation and the peak associated with the gamma oscillations, but we see much more lines, much more peaks that are obtained as a linear combination of the forcing frequency theta and the response frequency FR. So you see some peaks that are easily obtainable as linear combinations. So in order to get a power spectrum which is comparable to the experimental one, we have added some noise, thinking that the sources of the differences in the experiments is noise, is the inevitable presence of noise. And in fact, by adding some additive white Gaussian noise in our neural mass models, we are able to recover power spectra that are comparable to the experimental ones. Then looking at different power spectra obtained for different forcing frequencies in case of fixed forcing amplitude and in the absence of noise, we have tried to compare the experimental results that are given by the red dots with our numerical results, picking the position FR of the main peak for different simulations and for different values of the frequency of the stimulation current. In particular, we can see that we can see essentially that the experimental data show an increase which is proportional to the forcing frequency, while in the simulation, because the equivalent simulations are the blue the green squares, we see that FR has an almost constant value, and we are able to obtain a similar behavior as the one shown by the experimental results, just considering the subsidiary peaks FR plus no theta. On the other hand, if we look at the power of the gamma oscillations, as you can see here, we can see that the power remains essentially constant for low frequency values, and then it decreases for increasing values, both in the ping and in the ing setup, while the experimental results essentially show a resonance around 5 Hz. So this is one of the big differences between the two between the experimental results and our numerical results. So in order to cope with these differences, we have tried to add noise and to see what's going on if we add noise in the power spectra. So looking at the pink setup, we see that the noise renders the spectrum more flat and shifts the position of the peak in the gamma range towards higher frequencies, and that the position of the main peak is almost insensitive to noise up to small amplitudes, then it linearly increases with the amplitude of the noise A. On the other hand, if we look at the dependence on the force amplitude I0, we can see that the position of the main peak increases linearly with I0 and gives rise essentially to more defined peaks in the gamma range. But the results are not in agreement with the experimental results obtained by Butler and co-author in 2016, but let me say they are in agreement with some successive results obtained by the same group in a following paper of 2018. So to conclude, if we perform the same analysis that we have performed before, so calculating again all the position of the peaks for different value of the external frequency, of the external forcing frequency, we can see a reasonable, in this case, a reasonable agreement with the experiments both for the ping and the ing. Caveat, so noticing that we have to increase nu theta together with the amplitude of the noise or the amplitude of the external current in order to get results that are comparable with the experimental results. So to conclude, we have been able to, both for the ing setup and for the ping setup, we have been able to show that theta-nested gamma oscillation may emerge under an external excitatory drive. This is possible by choosing a system in the asynchronous state but nearby Hopf bifurcation, which allows the external forcing to drive the system across the bifurcation inside the oscillatory regime. The emergent gamma oscillations have an amplitude which is related to the distance from the bifurcation point. Two important things to notice. We have a perfect locking between theta and gamma redoms, thus giving rise to periodic behavior in the ping setup, and an imperfect locking in the ing setup. The ing setup shows that the lock states are more frequent in agreement so with previous literature. This is really the last slide, just discussing briefly the agreement and disagreement with the experiment. The agreement with the experiment is the possibility.
Sorry, Simona, your audio is very poor, I'm afraid. Do you mind just repeating this from the start?
Okay, so the very concluding slide is that a brief summary of the agreement and disagreement with the experiments. So in agreement with the experiment is the possibility to show the emergence of nested gamma oscillations that and the fact that the gamma power and the frequency of the gamma peak increase almost linearly with the forcing amplitude. The disagreement is that we are unable to reproduce the sort of resonance of the gamma power as a function of the external frequency, and the fact that we are obliged to assume that the stimulation power increases proportionally to the external frequency in order to get spectra that are similar to the experimental ones. So I stop here and I thank you for listening, because I see that there are also some problems. Thanks.
Thank you very much, Simona, for that talk. Yeah, please raise your hand if anyone has a question. I'm just going to jump in with a question about, I think it was on slide 16, Simone. You showed this really nice, these nice couple of pictures of some Arnold tongues showing the phase locking states. I think on the right is the for the ing setup. Yeah. So do these overlap? So is there bistability in these phase lock states here, or do they bifurcate at the borders?
Yeah, I mean, we did not look into the detail of eventual bistability, but the kind of transition that describes the subcritical Hopf bifurcation that allows to pass from the synchronous to the collective oscillation state is not hysteretic. So I do not expect that there are phenomena of bistability here. Probably there are small overlappings that we have not looked into, but I don't expect stability.
I see. Thank you very much. And I think Matthew's got a question.
Yes, quite fast. So it was more a curiosity. You said something about a chaotic point in your bifurcation diagram. I don't know. I wonder, is it some kind of gamma? Does it have some gamma oscillations or some bars, or it's just?
You can look at the activity here. For you can see you still have some gamma bursting, but the amplitude is chaotic in the sense you have some chaoticity in the amplitude of the oscillations.
And of course, the theta forcing is required to have this.
Yeah, because otherwise you are simply in the asynchronous state. And bigger is the amplitude of the theta forcing, higher is the probability to have some form of chaos. So I mean,
Oh.
I would say I cannot tell you that there will be no chaotic states also in the ping regime for higher value of I0, high values of I0.
Okay, I understand. Thanks.
I think we might have time for just one more quick question if anyone's got one. Otherwise, I'd like to thank. Oh, Etienne's got a quick question.
Yes, please, if we have time for one question. Simona, you told about introducing noise in your analysis of the spectrum. What kind of noise did you consider?
It's just, I know that Dennis will not agree on the introduction of, on this kind of introduction of noise, but it was, somehow it was the easiest way to introduce some noise without using the theory of cumulants that he has introduced. It's just white additive Gaussian noise.
Okay, so it's not a static noise.
Yeah.
Okay. Thank you, Simona.
Yeah, thank you very much, Simona. And now I'll invite the next speaker, Matteo De Volo. If you want to share screen, Matteo. And Matteo will give a talk on emergence of collective oscillations in neural networks due to endogenous fluctuations.
Okay, let me know if you see this. Does it
yeah.
work? Okay, good.
That's perfect.
Okay, so thank you very much for organizing this day and for inviting me to present these results. So in this talk, I will discuss about collective oscillations, which are similar to those that Simona has been talking about. But I will talk mainly about the impact of noise, but one form of noise which is endogenous in the system, meaning that this kind of noise is generated by the system itself. So first of all, I would like to say something about the spiking activity that we observe in the brain, in this case in the cortex. So there are different regimes. You can see asynchronous dynamics, or also some regimes which are more synchronous. So here is one raster plot. So whenever one neuron emits a spike at a certain time, we draw a dot. And you can see here, the spiking times of neurons are highly irregular, both in the asynchronous regimes and also during synchronization. So whenever, even if we have at the global field, at the population level, some global field which is oscillating at the larger scale, at the microscopic scale, neurons still have a very irregular, Poissonian-like in general, spiking activity. Nevertheless, the brain is able to organize a coherent population activity that, depending on the state of the brain, shows different collective dynamics. We can have some asynchronous dynamics, but we can also have some oscillations, as Simona has been showing. So we can have some different attractors and different dynamics at the collective scale, while at the microscopic scale, neurons appear to be very irregular. So what I will do is that I will try to study the impact of this microscopic irregularity for collective activity using a model, in particular the quadratic internet-fired neuron. So V is the membrane potential of neuron I, and it follows this differential equation where this is the an external synaptic current. Whenever the neuron arrives to infinity, the neuron emits a spike, and then it is reset to minus infinity. So what we can see is that in the case that this current is constant in time, imagine a parameter, whenever this current is positive, we have some periodic activity of the neuron. Whenever this current is negative, the neuron doesn't emit spike, it is silent. And whenever this current is 0 plus some white noise, in this case, it's a Gaussian noise, you can see that the neuron will emit spike in an irregular fashion, similar to what we see in the brain. So, but neurons are in a network in the brain. So we will study a network of these neurons connected together. So we have one parameter, which is this external current, which is the same for all neurons, plus this synaptic term, which is the fact that neurons are connected over a random graph, where epsilon ij is the matrix of connection. It is 1 if neuron j sends an input to neuron I and 0 otherwise. Well, this delta means that we have an instantaneous interaction between the neurons. Whenever the neuron j emits a spike, immediately the voltage of neuron I is decreased of a factor 2g. It is important to notice that here I'm considering an inhibitory network. So neurons, when your neuron emits a spike, it inhibits the other neurons. Okay, so notice that this model is completely deterministic. There is no noise in this model for the moment. So we will have one important parameter is the average connectivity of the network, which is k, and then we will consider a distribution of connectivities that follows this Lorentzian distribution. Okay, so we have this random graph, and what is important and I wanted to stress here is that we will choose to scale the external current, which is something positive, and the coupling between neurons in this way, which is a famous scaling for to obtain a balanced state. Let me explain why. Indeed, if you consider one neuron and you consider the net current that the neuron receives, on average, this current can be approximated in this way. So R is the mean firing rate of the system. So there is this term, which is I0 multiplied by the square root of k, and this term, which is G0, the mean activity multiplied by the square root of k. This is just a consequence of our scaling. But if we make the assumption that neurons emit spikes in a Poissonian way, the fluctuations of this mean term will be finite and will be proportional to the coupling strength and the firing rate. So what you can see is that in this situation, the only possible solution for k going to infinity is a balanced solution. Indeed, imagine that this current is positive. When k goes to infinity, the neuron will receive an infinitively positive input. And as the network is inhibitory, R will go to infinity, and then I will be negative. On the opposite, if we assume I positive, we will have that the firing rate will go to 0, and then that I will be positive. So we reach a contradiction. So the only possible solution in the limit of k going to infinity is a solution where this current is 0, and as a result, the firing rate of the network will be I0 divided by G0, because this term should be 0. But in this limit, what is important is that fluctuations, so the fact that those that are endogenous fluctuations in the network, due to the fact that we have that the connectivity K is much smaller than the size of the network, we stay alive. So I will study this model, which I repeat is a deterministic model, and I will want to study the collective oscillation and how they depend on the irregular activity of neurons. Noticing that in the brain, we observe a broad range of frequencies, and we want to study indeed what is the role of neurons' irregularity for collective oscillations. So we take the model that I have introduced, and we make a simulation. Here I will show you the results of a simulation for quadratic internet and fire neurons, but this phenomena can be observed also in different models. I don't want to enter into the details, but here I will report always in blue generally the results for another model, which is the Morris-Lecker model. What you see here is that the network exhibits some regular pattern, which are these quasi-synchronous events. And if you look at the population activity, which is the mean voltage of the the population firing rate that we have been listening before, you see this periodic oscillating activity. So we have collective oscillations, but if you look at individual neurons, neurons have an irregular firing pattern. So these bars are not always the same. At each time, there are different neurons that participate, and neurons do not always lock to the global field. Neurons are not locked to the global field. So we wanted to study this phenomena, the emergence of this phenomena, and what we can measure is some parameters of synchronization or coherence. Rho is 1 when the system is synchronized, coherent, and rho is 0 if the system is asynchronous. What we see is that for both models, whenever the connectivity K of the system increases, rho, there is a transition, a bifurcation from an asynchronous regime to a synchronous regime. And importantly, the coefficient of variation of the neurons that measures the irregularity of neurons, when the CV is 0, it means that neurons are periodic or silent. When CV is 1, it means that the spiking statistics of the neurons is Poissonian. You see that the CV is always quite high in the network, but we have both asynchronous and oscillatory regimes. More interestingly, if we vary some parameter in the model, we can see that here I change, for example, the level of heterogeneity in the connectivities or the external current. We see that whenever the coefficient of variation that measures the irregularity of neurons goes to 0, also synchronization goes to 0, which gives us an idea of the fact that indeed this irregularity of neurons, which is the source of the endogenous noise in the system, is necessary for coherence, so for the emergence of oscillations at large scale. If neurons, in an intriguing way, if neurons are regular, then there is no coherence in the system anymore. The coherence, the collective oscillations appear only if neurons are irregular. So if you want to start to make a mean field theory of this system, the first thing that we can do is to perform some kind of heuristic mean field theory. So just writing down a transfer function of the system, and we end up with a one-dimensional differential equation for the population rate, imaging some kind of Wilson and Cowan model, and which never shows collective oscillations. So what we can do is instead is going back to the input that neurons receive. So this is the matrix of connection, this is the spikes. And you know that if the connectivity is sufficiently large, we can make the hypothesis that this term will be proportional to the in degree of this neuron I multiplied by the mean activity of the system. But this is not enough, because on top of it, there will be fluctuations due to the fact that neurons, that the number of connectivity K is finite. And if we assume that neurons have a Poissonian statistics, we can also estimate the amplitude of this effective noise, which is self-generated by the system, which will be proportional to the square root of the firing rate. This is just a consequence of a Poissonian firing statistics of the neurons that we are assuming here. So altogether, if you can see, we can this current can be effectively described as a mean term, mean field, plus some endogenous fluctuations. So altogether, this model in this assumption is equivalent to an all-to-all system, because the coupling is global, with disorder in the couplings, because each neuron has a different connectivity, which is equivalent in this case to have a different couplings, okay, plus noise. So for this system, if we imagine that we have a distribution of couplings which is a Lorentzian, we can write down a continuity equation, which is this one, where W is the probability density function of my system. this is the continuity equation for the class of neurons with coupling J. Notice that here there is also the term due to the presence of this endogenous noise. So the system still is deterministic, but it is described with this effective noise term. R is again the firing rate of the system. In the specific case of sigma equal to 0, we know that we can use the Hot-Hamptons and Ansatz that has been applied to Keith neurons by Monbrieux and colleagues, and we can have an exact solution of this equation for sigma equal to 0. So for the moment, let's imagine sigma equal to 0. What happens if we completely forget about sigma? Well, we end up with a two-dimensional mean field model, okay, for the population rate and the voltage that we can study. In the case of a fixed point, we can estimate the value of the fixed point, and we see that for this model, indeed, we find back the fact that in the limit of k that going to infinity, the firing rate of the system converges to the balanced solution, A0 divided by G0, as I was saying at the beginning. And this can be seen also here, where you see that in red is the firing rate predicted by this formula, okay, that goes to I0 divided by G0 in the limit of k that goes to infinity, and black are just the simulation of a network of neurons. As you can see, of course, in the network of neurons, there is some noise indeed, and so the agreement is not perfect, but it's quite good. But then you remember that in our system we had oscillations. But if we perform a stability analysis of this system, we always find stable focus. So this model never shows collective oscillations. So what we were thinking is that indeed we have this stable focus in the non-noisy system, and the role of noise, the endogenous source of noise, is to excite the relaxation toward the stable focus and gives rise to these sustained oscillations. To verify this prediction, we can estimate the frequency of the stable focus analytically from our model and compare this frequency with the frequency of collective oscillations that we see in the network. And indeed, what you can see here is that we find that the frequency of the collective oscillations predicted by this stable focus is this red line in function of the current and not of conductivity. And you can see that black circles are the network simulation. You can see that it works quite well. So indeed, we have not a demonstration, but an indirect evidence that these collective oscillations are due to the endogenous noise that the system generates due to the balance between excitation and inhibition. Notice that here the frequency of these oscillations is very interesting because it covers a very broad range. It goes from 0.1 Hertz up to 100, just changing continuously one parameter. So we have a very interesting kind of oscillations. Then, I don't want to enter too much into the details. We can extend these to excitatory and inhibitory networks. In this case, the model will be 4-dimensional. So we have two frequencies, so a focus characterized by two frequencies. And then we will have, in this case, as predicted by the theory, quasi-periodic oscillations in the network with two fundamental frequencies that can be very well, as you can see here, very well predicted by our stability analysis based only on the non-noisy case. So you can see here that, of course, the prediction of the mean field are not perfect. This is because sometimes in the network we observed some locking between the frequencies, and also because you need to remember that our model is approximated, because we have completely forgot about this endogenous noise that is present in the system. Okay, so I want to finish with what we could do now instead to solve our main problem, which is the fact that our model does not show collective oscillations. So we go back to our Fokker-Planck equation, okay, that, as I told you, in the case sigma equal to 0 can be exactly solved. Okay, we can find an exact solution, which is the octantons and ansatz. But in presence of noise, the octantons and ansatz doesn't hold. Okay, and what we can do is that we can write down the equation, noticing that the noise term in our model is different for each neuron with coupling J, and is proportional to the J square multiplied by the firing rate. So the system is quite complex also because the amplitude of this noise, which is a noise that is self-generated by the system, changes in time, because in principle the firing rate is a function of time. And not only, this noise is also noise that depends on the neuron. So there is an heterogeneity of noise amplitudes, even if this is a system that can be in principle solved thanks to numerical simulations. So we can anyway perform numerical simulations to check if this system, this Fokker-Planck equation model, correctly predicts the dynamics of the network. And this is what we are working on. And I can show you here some preliminary results where we see that indeed, here is a simulation of the network. Rho is the synchronization and K is the connectivity. Again, you can see that we have a transition from asynchronous to synchronous dynamics. And you can see that simulating the Fokker-Planck equation, predicts the existence of a Hopf bifurcation from a fixed point to a limit cycle. So having a Fokker-Planck that takes into account this endogenous noise term is enough, even if it is not perfect, because as you can see, the bifurcation point is not perfectly reproduced by the Fokker-Planck. Even if it is not perfect, it still permits to predict the emergence of these oscillations. And you can see here also the fact that if we compare the firing rate of the network in time from different network simulations at different sizes with the Fokker-Planck model, we can see that the Fokker-Planck model correctly predicts the network simulation. Remember that anyway, this Fokker-Planck model has a infinite dimension in principle, so it is very far away from the simplicity of the neural mass model that I have discussed before, but that was not able to show these oscillations because it was not able to take into account the endogenous noise, which is responsible for the emergence of these collective oscillations. Okay. So let me go to conclusions now. So first of all, I have shown that in a network model, which is completely deterministic, we can have the emergence of collective oscillations, so periodic limit cycles in population dynamics, which are due to the presence of a form of endogenous noise, which is due to the sparseness of the connections in the network. So the fact that the connectivity is much lower smaller than the number of neurons induces some endogenous noise in the system, due also to the balance between excitation and inhibition, which is responsible for the emergence of collective oscillations. On the other side, whenever neurons are regular and there is no noise in the system, endogenous noise in the system, there is no synchronization in the network. This type of oscillation can cover a very broad range of frequencies by changing continuously the parameters of the model from 0.1 up to 100 of Hertz. And then I showed you that a zero order neural mass model, in the sense that if we neglect the noise term due to the network sparseness, is able to predict very well the asynchronous dynamics and the frequency of the collective oscillations, but not the emergence of collective oscillations, which is instead well reproduced by the complete Fokker-Planck equation, so a model which is infinite dimensional that takes into account the fact that there is this endogenous noise in the this endogenous process in the dynamics of neurons, which comes from the sparseness of connections. So the goal now is to perform, is it possible to determine a reduced model following the steps of similar to the Monbiot and colleagues model for the system with the noise that can be external or endogenous in the networks. This is what we will Dennis Goldobin will speak in the next talk, and you will see that it is possible to use to derive a low-dimensional reduction method to have a neural mass model for these sparse and noisy networks of neurons. So I need to thank the collaborators to this work. So Marco Segneri, Dennis Goldman, who will speak after me, Antonio Politi, and Alessandro Torcini, and some of these results can be found here in the talk by Dennis, and hopefully very soon in this work in preparation. And then I'm done, and I thank you for your attention.
Thank you very much, Matteo. Do you have any questions? I'm just going to ask one, and about the the shape of the noise that you use, the distribution that you draw the noise from. Are your results very sensitive to that distribution, or could you choose that distribution still generate very similar collective oscillations?
Okay, yes, that's a good. You mean the distribution of noise?
Yes, yeah.
So in my case, actually, the noise is something that is generated by the system itself. So I am just trying to guess and making the hypothesis that it is a white noise, and that its amplitude, if neurons spike as in a Poissonian-like way, I make the hypothesis that the amplitude of this noise follows this law. But in principle, with the Fokker-Planck equation, we can do whatever we want. And here, as you will see in the next talk by Dan, is that if you consider a noise which is not, which is external, and you add noise to the system, you still need a finite amplitude of this noise to have oscillations. If sigma is 0, you do not have them. But if sigma is over a critical value, you have oscillations. But it is not necessary that it depends on the firing rate as the endogenous form of noise. So even if the additive noise can generate oscillations.
Right, I see. So it's truly.
This you will see. But we didn't study a different distribution of the noise. We just studied the Gaussian white noise.
I see. Thank you very much, Matteo.
You're welcome.
And I'll go over to Thilo for a question.
Yeah, thanks for the nice talk. I wonder about the Poisson assumption. Do you see cases where this Poisson assumption may lead to some larger deviations. So how valid or how useful is this Poisson assumption for the final quantities that you compute? If in case maybe where the statistics at the single neuron level is not very Poisson. So is the Poisson approximation then still good, or would it have some effects on the collective dynamics?
Yes, that's very good. That's a very good point. Thanks. So it has an effect indeed, and in principle, this amplitude of this noise that I have been talking about should be multiplied here by the coefficient of variation of neurons in general. If CV is 1, it becomes the usual Poissonian, but then if CV is 0, then this amplitude of noise is 0. If you do this, and we can see that typically the CV is not exactly 1. And here I show you some results when if we change the CV of neurons, instead of 1, here I use 0.8, for example, which is what I see in network simulations. You see that the critical value of the connectivity changes a bit, which is this. So indeed, it has an effect, but what we have, so that's why also the agreement is not perfect. But still, using CV equal 1, I have seen that across the parameters range is quite a good approximation. It works quite well in principle.
Mm-hmm. And does a simple rescaling of the noise with the CV would solve this problem? Because in general, it does not only depend on it depends on the autocorrelation function of the spike train, not only the CV.
Yes.
But do you observe that you can do the simple rescaling of the noise with the CV and it works?
Yes, yes. This is, at this order of analysis, yes, because here actually this CV is what I have taken from directly numerical simulation, and I have seen that it worked quite very well in this situation and also in others. So, but then, and this is this dynamical regime where maybe in different dynamical regimes it may be different. This is an interesting question. I don't know if the process will not be of this kind. I think that it can be different, but it could maybe be taken into account in the Fokker-Planck equation somehow. Still, I think.
Thank you.
Well, thanks.
I mean, you have colored noise and not white noise anymore, and this stuff, right?
Yeah,
but
yeah.
okay.
Yeah.
But thank you.
Exactly.
We do have just one more question in the chat, Matteo, but I think in the interest of time, it's probably best to go on to our next speaker. But if you could, if you want to answer this question from James Poe in the chat, Matteo, after the next talk, then.
So
then,
yes, I think it is
ahead.
about the. I think it is about the Lorentzian, if I have correctly seen the question. So yes, so it depends on the parameters of the Lorentzian distribution. For example, whenever the width of the Lorentzian distribution is too large, we do not have oscillations anymore. So there is a bifurcation in function of the amount of heterogeneity in the system. But then we have seen that the phenomenon can be observed, the same phenomenon also in a completely homogeneous system, also so without only with all neurons have the same connectivity, so there is no Lorentzian and nothing else. And also we have seen that we have a very similar behavior if instead of the Lorentzian we use a Gaussian distribution. But this is but then I mean, for this phenomena it doesn't seem to affect the results, but then maybe for other phenomena I know that it can affect the results. Yes.
Thank you. And now I'm going to hand over to our final speaker of the day, Denis Goldubin.
Thank you so much for invitation to this conference, and also thank you very much, Matteo, for your introduction. So, just a second. Do you see my? Can you see my screen well?
Yeah, we can see it fine.
Thank you so much. So I will talk about reduction methodology for fluctuation-driven population dynamics, and specifically when we go beyond the Laurentian or Cauchy ansatz, which is also somehow related to Ott-Antonsen ansatz. Laurentian distribution or Cauchy distribution quite frequently emerges in different problems in statistical physics and theoretical physics. Examples of this is laser theory, where Laurentian distribution naturally emerges. Also, Laurentian distribution allows to solve some in-field problems, employing the residue theorem to calculate integrals analytically in general. Another example in statistical physics is so-called Lloyd model. It is the only solvable example of Anderson localization in 3 dimensions. So all other results are either not that much well solvable, or I mean not in that not so deeply solvable, or one-dimensional. So it's very important also to have something in multiple dimensions. And another example, which is much closer to our experience, to the experience of people who are participating in this conference, it is Ott-Antonsen ansatz. In this case, we have Ott-Antonsen ansatz actually corresponds to rapid Laurentian distribution of phases. And also Monbrio, Pazzo, and Roxin, they were considering quadratic integrated fire neurons, and showed that for Laurentian distribution of voltage for these quadratic integrated fire neurons, one can derive and rigorously derive an exact mean field model, which actually also related to Ott-Antonsen ansatz. What is, however, the problem with Laurentian distribution? For Laurentian distributions, distribution or moments diverge. So it means that we actually cannot, it is not obvious how you can work with perturbation to, or some deviation from this Laurentian distribution. At least you cannot work in terms of moments. However, you can work in terms of characteristic function, probably. And when you have characteristic function which is determined like that, you can also introduce cumulants for these moments via so-called cumulant generating function, which is logarithm of characteristic function, this phi, and you just have coefficients of similar Taylor expansion and their cumulants, like here, their moments. Why cumulants are, or at least previously in literature, they were called sometimes semi-invariants, why they are so much useful? The first cumulant, it is just the same average value, the first moment, but the second cumulant, it is already something where you extract trivial information from second moment. So you take the variance, in fact. And so on, you can, for higher order cumulants, you just have something which removes trivial information from previous order. Here we remove the information about the average value, and here we remove the information about both the average value, the mean value, and the variance. And another, what is good about cumulants is that if we have 2 independent random variables, with moments, you can only first moments are additive. For higher moments, for instance, if you consider x plus y and mean square value of them, you have already something which is more sophisticated. But for cumulants, for any order of this cumulant, if two variables are independent, you have additivity of these cumulants of any order. So for many physical situations, for many practical situations, it can be very convenient to work in terms of these cumulants, not in terms of moments. But as I mentioned, moments are diverging for Lorentzian distribution. And why one cannot work with characteristic function itself? If you look at characteristic function for Lorentzian distribution, it is such an exponential. The imaginary part here is just with k, and the real part, it is here with absolute value, with modulus of k. And characteristic, cumulant logarithm of characteristic function for this Lorentzian distribution, it is even more simple. You have something which is almost linear, just different coefficients for positive and negative k. The imaginary part is pure linear, and real part is this modulus of k. Let us try to apply, well, let us at least try to consider the population of quadratic integrated fire neurons and see whether we can have something useful with this characteristic function for this system. We have usual quadratic integrated fire model where input current have some common part for different oscillators. It is this part. We allow for some heterogeneity of properties of these neurons, and we also allow for, we also introduce noise in our system. It's Gaussian, delta-correlated Gaussian noise. Without this Gaussian noise, one can apply here or Tantonson or Monbrio, Pazzo, and Roxin mean field models, but this red term, this noise, it violates applicability of these reductions. And here we also have some input, and G is coefficient for this input, for this synaptic input. In the thermodynamic limit of large population, this synaptic input will be just population mean firing rate, or at least something which is very close to that. One can write down Fokker-Planck equation for the probability density of eta subpopulation, so subpopulation which is characterized by given value of this eta, and this is here it is this Fokker-Planck equation. And I remind what is E sub eta in this case. Now we can consider characteristic functions for specifically eta subpopulation. It will be such an integral, such an average value. And we can consider time derivative of this characteristic function. Here we will have this time derivative, and we just substitute this time derivative from Fokker-Planck equation, which I showed previously. And we end up, after some algebra, we end up with such an equation for this characteristic function for eta subpopulation. One should be careful with derivation of this thing because there are some issues of calculation of these integrals because their convergence is not so well, but nonetheless one can do all these things rigorously and end up with such an equation. If we now consider entire population, we introduce characteristic function for entire subpopulation in such a form where G of eta is a distribution of this eta. And for Lorentzian distribution of this eta, we end up with such an equation. One should be careful when do this because when you apply the residue theorem, you should take different arcs for negative and positive k because they, in one case, they will converge in upper half plane. In another case, they will converge in lower half plane. And this is why we have this modulus of k here. So we have different cases for positive and negative k. All other terms are not sensitive to this thing. So we have such an equation for characteristic function. And again, because we remember that characteristic function for Lorentzian distribution is some exponential, and it is much better to work with logarithm of characteristic function. Let us here also consider logarithm of characteristic function, this phi. And for function phi, we find such an equation. You can see that we have a couple of terms here, and these three terms, they are very simple. They do not contain phi, and this is just linear thing, some modulus, and some quadratic thing. So without this quadratic term, Lorentzian distribution is admitted by such an equation, so we can just substitute such a linear thing. Imaginary part is linear, real part is modulus k, and it will solve this equation, because for this term it will be just constants. This term will disappear, almost disappear, but it will be a delta function, but undangerous delta function. So you can consider it disappearing because it is multiplied by this k. And here this is this thing. So everything is just satisfied, and we end up with Monbrio, Pazzo, and Roxin macroscopic model for this quadratic integrated fire neurons, where it is related to firing rate of this population. However, when we have this quadratic term, such a linear substitution will not work anymore, and we should consider something else. In fact, for this equation, we just can consider a most general form of this function, of this logarithm of characteristic function. We just introduce all possible powers of k. And we should be careful, because by definition, by how this function is constructed, it must obey such a symmetry. If we change the sign of k, we just must have a complex conjugate here, and it actually means that for some terms, imaginary terms should have one symmetry with respect to k, and pure real terms should have opposite symmetry with respect to k. And we must have such an alternation of these sign things here. So when we have just this thing, it means that we have simple power term, and for this term it is just we take modulus of k here, one of multipliers, and this is similar to this situation. Now we can introduce so-called pseudocumulants for this case. For this case where neither moments nor cumulants exist, we can introduce these coefficients, and we can call they are somehow similar to cumulants, so we call them pseudocumulants. The first pseudocumulant, it is just this thing which was present in Monbrio, Pazzo, and Roxin model, and here also some higher order terms. And we can find such an equation for this, such an infinite equation chain for these pseudocumulants. And we can actually have geometric interpretation for these pseudocumulants. So A and V are always, at least for quivs, A is always related to firing rate, and it also characterizes the width of the distribution. V is always the median of the distribution. So even if higher terms are present, V will be always the median of the distribution. The mean value can be shifted in some cases, but the median will be just given by this V. And Q2 will be an analog of kurtosis for Gaussian distribution, and P2 will describe asymmetry of this distribution. And if we are not working with some distortion of Lorentzian distribution, if we have something else, if we have some case where some moments can exist, and if the moment of order n is existing, in that case, for even n, all lower p sub n will be 0, and q sub n for odd n will be 0. And the remaining parts of these things, so we will, for all terms, we will have just these simple things without the sign part. They will be just related to conventional cumulants at moments. But above this moment, which is finite, we will have both real and imaginary part for all these pseudocumulants, and they will not be anymore connected to conventional moments at cumulants, not to mention that they will diverge. So we can try to apply these equations for some examples. Let us introduce noise into Monbrio-Pazzo and Roxin model, and in that case, we can consider two cumulant approximation, two pseudocumulant approximation, two original equations by Monbrio-Pazzo and Roxin, and additionally a couple of equations, and we can actually approximate in a lot of details in using this theory. I will not go into these technical details, but it is possible to get a lot of information with this pseudocumulant model reductions. And similarly for Ratos and Piragas work, where they consider noise and finite duration of the firing events, we will have just this sort of model again, and the firing rate S should be replaced with such a construction, which is just a technical thing for the theory. It is essentially doable. And another examples, one can employ this mean field theory for the balanced networks, balanced spiking networks with sparse network of connections. And here we have, as Matteo explained, we may consider an effective noise. The intensity of this effective noise will be given by these terms. It will be related to firing rate, and with these equations we may have some mean field description, which actually yields us collective oscillations, which is able to reproduce these collective oscillations Matteo was mentioning. And also, I want to touch briefly the issue of convergence of these expansions and truncation. If we have non-zero heterogeneity and non-large and are not very large, not very far from time-independent states, in that case, we can explicitly show that we must have such a nice hierarchy of smallness for these cumulants. Here you can see this hierarchy with exact solution of the equations in the thermodynamic limit, of course. Here you can see that higher cumulants, higher pseudocumulants follow this scaling very well, and it means that we can neglect higher order terms when they are not needed. We can consider, for instance, only leading terms. If we do not have this perfect condition, I mean, when we have some heterogeneity and not very far, we still have some sort of hierarchies of smallness for these pseudocumulants, but there it can be more difficult, more challenging to prove, to derive these scalings analytically. And here I would like to show briefly the results for this finite large network of quadratic integrated and fire neurons with sparse network of connections. We can with this model, we can calculate in time-independent states. We can calculate firing rate, mean voltage, and these characteristics, and compare them with network simulations. Symbols show the network simulations. Here, these symbols show the calculation of higher-order pseudo-cumulants specifically for the states of this finite ensemble. We just were taking the state of ensemble of 10,000 elements, considering their distribution and calculating a characteristic function and all these things. And here you can see dots are results of network simulation, and solid lines are results of running of this mean field model. And here it is how we can reproduce very well our microscopic observations with this model. And so I come to conclusion. One can introduce pseudo-cumulant formalism on the basis of characteristic function for dealing with perturbed Lorentzian distribution, actually not only for this neuron networks, but also in many diverse other physical problems. This formalism yields generally convergent infinite mean field equation chains, which can be truncated, generally can be truncated, or at least approximately it can be truncated always. It yields us low-dimensional mean field models, which can be derived for microscopic dynamics. Well, okay, you can use them for practical problems. And in particular, one can rigorously treat the attractivity of the Otatotzen or Montbrial-Pazar-Roxin manifolds with these low-dimensional models. You do not deal with infinite-dimensional Fokker-Planck equation to treat transversal stability of these Otatotzen and Montbrial-Pazar-Roxin solutions. And well, as I demonstrated, we can also reproduce the results for finite networks very well. So thank you very much for your attention. And the results will be shown, will soon appear in PRL. Here. Thank you so much for your attention.
Questions? I've just got one about the so you use these sort of perturbations in the Lorentzian as an analog for the noise, but how much leeway do you have? Could you for instance have say a double peak in the Lorentzian or something like that to generate multiple frequencies?
We can consider the multi-peak distribution. So the essential part, well, the essential step which was most challenging, it was this one. Sorry, having such an equation for eta subpopulation. So if we have this, after that, at least for eta subpopulation, we can do everything. We can construct our mean field models, and then this eta, it can be Lorentzian distribution, it can be multi-peak distribution, it can be anything. Just in case if it is Lorentzian distribution or it is some superposition of several Lorentzian distributions, we have some specific sort of equation, some specific equations for this function f for entire population. But even in the case if we are not able to switch from this equation to this equation, we can still consider a set of such equations for each value of eta, for several values of eta. I mean, this eta, it can be frequency of individual neurons or whatever you want. And then you can construct this thing. If you mean that you want to consider a multi-peak distribution for for states, for voltage, for instance, of individual neuron, it can be already, well, formally it can be done, because what we do here, we consider the most, we have this equation for logarithm of generating function, and we consider the most general form of this generating function. It can be, well, it actually covers whatever you can have. The another problem that it can be not so very well convergent. So you may need, for instance, 10 or 20 terms or something like that. It is like usual. So for instance, for Lorentzian distribution, Lorentzian is this term. And if you are not far from Lorentzian distribution, you just need few terms to be close to this real distribution. But if you have some complex shape here, you will need to keep a lot of these power terms. But anyhow, any function, any smooth function, sorry, any continuous function can be approximated by polynomial with given accuracy. It is even stronger than just having Taylor expansion, because Taylor expansion, it is not always convergent. But for some given function in some interval, you can always have polynomial approximation with given accuracy. And in this sense, such a thing, it can be even stronger. Another problem that you have very poor convergence. You may need a lot of time, but generally it is doable. Essentially, it is doable.
I see. Thank you very much for that answer, Dennis. I think it's 3 o'clock now. So on the channel 1, we've got the Microtalk session, which Etienne's just provided the link to. So at this point, I'd just like to thank all of our speakers today again for a fantastic set of talks. And yeah, please enjoy the rest of the conference. Thank you.
Thank you.
Thank you so much.
Thank you.